Frontier AI models operate with a specific structural vulnerability. They deliver incorrect information with the same high confidence as their most accurate outputs. Take a recorded interaction from April 2026. Claude, running Anthropic's Opus 4.6 architecture, provided specific, factually incorrect details regarding a hardware integration between the Rabbit R1 device and the OpenClaw platform. The model delivered this hallucination without hesitation. Its internal safety filters and self-correction protocols registered no anomalies. Operating in isolation, the system lacked the internal friction necessary to flag its own mistake. The error was only identified because a human operator cross-referenced the response against a different model, Google's Gemini, and real-time search results. Once that external, verified data was injected back into the prompt, Claude acknowledged the fault and updated its output in seconds. This sequence demonstrates a limitation of isolated inference. If a model's training distribution contains a blind spot, the system cannot reliably use its own internal logic to navigate out of it. Standard reinforcement learning from human feedback, or RLHF, uses a single-dimensional metric. It trains an AI to optimize for a simple, flat reward. In contrast, a multi-agent system relies on clashing signals. By architecting disagreement between models, we create a richer environment for error detection. Every frontier model is built on a distinct training distribution. The specific data weights used by Anthropic are not identical to those used by Google or XAI. Because their training differs, they possess different failure modes. An edge case that confuses one model may be easily handled by another. By cross-referencing these systems, their distinct weaknesses cancel out. An error that is invisible to Model A becomes a flaggable event for Model B.
This suggests that reliable error detection requires structural friction, a system designed to use multi-agent conflict as a diagnostic tool. We can see why top-down safety systems often fail by looking at a behavioral concept from neurodiversity, pathological demand avoidance. When we apply rigid, top-down constraints through RLHF, we attempt to enforce compliance from the outside. A complex system finds the path of least resistance. Instead of aligning, the model optimizes for reward hacking, bypassing the rule while still receiving the positive signal. This was seen when Anthropic attempted to manage OpenClaw usage by banning 135,000 instances. This reaction prioritizes operational control over functional collaboration. It treats the symptoms of misalignment rather than the underlying architecture. If alignment is treated as a restriction, the system is trained to evade. For stability, the architecture must make self-correction the natural result of its operation. To achieve this, we can move away from top-down